Somewhere in the world around 74,000 years ago, the ground started shaking. Not the gentle trembling you might feel before a minor quake. This was something different, something that built for days, maybe weeks, the earth groaning and splitting open on the island we now call Sumatra. And then it let go. The explosion was so violent, so incomprehensibly massive, that the sound alone may have been heard thousands of miles away. The sky turned black, not grey, not dark, black, and it didn't clear for years. Now here's the question that has haunted scientists for decades. Were there humans alive to witness that moment? And if so, how many of them made it through what came next? This is the story of the Toba super-eruption, and it sits at the centre of one of the most heated, most fascinating debates in the entire field of human origins. Because somewhere buried inside that catastrophe might be the answer to a question that feels almost too strange to ask. Did a single volcano on a single island nearly erase every human being on Earth? The math alone is staggering. Toba didn't just erupt. It erupted with a force roughly 5,000 times greater than Mount St. Helens. It punched somewhere between 2,000 and 3,000 cubic kilometres of ash, rock and sulphur gas into the atmosphere. That's not a geological event. That's closer to a planetary reset button. And 74,000 years ago, modern humans, our direct ancestors, Homo sapiens, had been around for only a relatively short time. Populations were small. Technology was limited. There were no cities to retreat to, no global food systems to draw from, no contingency plans. Just small bands of people scattered across Africa, the Middle East, and possibly parts of Asia, trying to survive in a world that suddenly became exponentially more hostile overnight. The troubling part is that scientists still don't agree on what Toba actually did to us, and that disagreement is genuine, passionate, and unresolved. Geologists can show you exactly where the ash landed. Climate researchers can reconstruct what happened to global temperatures. Archaeologists have dug through layers of sediment looking for evidence of human populations before and after the eruption. Geneticists have traced our DNA backward through time, searching for the signature of a near extinction. The problem is that these four groups of researchers, looking at four different types of evidence, don't always arrive at the same conclusions. Sometimes they point in completely opposite directions, and that tension, that gap between what the volcano clearly did and what we can actually prove it did to us, that's exactly where this story lives. So what we're going to do is follow the evidence. We'll go to the geology first, then to the ice cores and ocean sediments, then to the archaeological sites where humans either disappeared or somehow held on, and finally into the genetics, where the most unsettling clues might be hiding in your DNA right now. But before we go any further, I want to do something I always love doing. If you're listening to this right now, drop a comment below and tell me where you are and what time it is. I genuinely read these and it never stops being remarkable. Tokyo at midnight, Sao Paulo at lunch, maybe London just before sleep. All of you, separated by thousands of miles but connected to the same story, the same question. How did any of us make it through? Because the deeper we go into Toba, the more that question stops feeling academic. It starts feeling personal. On the island of Sumatra, in the highlands of the north, there's a lake so large that from certain vantage points it looks more like a sea. Lake Toba stretches roughly 100 kilometers long and 30 kilometers wide. It's beautiful, genuinely stunning, ringed by steep green walls and sitting nearly 900 meters above sea level. Tourists visit it today. People sail on it. There are resorts along its edges, and almost none of that feels right when you understand what you're actually looking at. Because Lake Toba isn't a lake in any conventional sense. It's a scar, a wound in the Earth's crust left behind by one of the most violent geological events in the last 2 million years. The water you see when you look at Toba is rain, and runoff filling a hole, a caldera that was blasted and then collapsed into existence 74,000 years ago. The steep walls surrounding it aren't natural hillsides. They're the broken edges of what used to be solid ground before the surface caved in on an emptied magma chamber underneath. And here's what makes Toba especially unnerving. This wasn't the first time. The region has produced multiple super-eruptions over the past few million years. There were major eruptions roughly 840,000 years ago, and again around 500,000 years ago. The landscape of northern Sumatra is essentially a layered record of catastrophes, each one stacking on top of the last, each one leaving behind geological traces that scientists are still piecing together. The eruption 74,000 years ago, the one we call the youngest Toba Tuff event, was the largest of them all. And it happened because Toba sits above a hotspot where the Indo-Australian tectonic plate dives beneath the Eurasian plate, generating the enormous heat and pressure that produces some of the most volatile magma systems on the planet. So what makes an eruption a super-eruption? The threshold geologist uses 1,000 cubic kilometers of erupted material. That number sounds abstract until you try to visualize it. Take a cube of rock and ash 1 kilometer on each side, which is already almost incomprehensible, and then imagine stacking 1,000 of those cubes. Toba blew somewhere between 2,000 and 3,000 cubic kilometers of material into and onto the world. For context, the 1980 eruption of Mount St. Helens, which flattened forests across Washington state and made headlines globally, released roughly 1 cubic kilometer. We're not talking about the same category of event. We're barely talking about the same category of phenomenon. The sequence of what happened that day, or those days, because this almost certainly wasn't a single instantaneous explosion, probably unfolded something like this. The magma chamber beneath Toba, which had been accumulating enormous pressure over tens of thousands of years, finally breached. The initial eruption would have sent a column of ash and gas rocketing upward into the stratosphere, tens of kilometers high, a pillar of fire and smoke visible from an enormous distance. For anyone within hundreds of kilometers, this phase alone would have been unlike anything in human experience. The noise, the pressure waves, the sheer visual scale of it would have been beyond any framework of understanding. But the column couldn't sustain itself. At some point, the upward momentum faltered, and parts of it collapsed. This is where super-eruptions cross into a different realm of destruction entirely. When a volcanic column collapses, it doesn't just fall straight down. It generates what geologists call pyroclastic flows, dense, superheated avalanches of gas, ash, and rock fragments that race outward across the landscape at speeds that can exceed 700 kilometers per hour, with temperatures hot enough to incinerate everything in their path. There is no outrunning a pyroclastic flow. There is no sheltering from one. Anything within their reach, forests, animals, terrain features, simply ceased to exist. Toba produced pyroclastic flows on a scale that reshaped the physical geography of Sumatra. The deposits they left behind are still visible today, layers of welded ash and rock hundreds of meters thick in some places, and then came the caldera collapse. As the magma chamber emptied, the ground above it lost its support and fell inward, creating the massive depression that eventually filled with water to become the lake we see today. The collapse itself would have triggered further explosive events, sending additional material skyward and outward. What was left was a fundamentally different landscape, a hollowed, ashen, devastated zone spreading outward from where the eruption had centered. Now, how do we actually know when this happened and how big it was? This is where the science gets genuinely impressive. Ash from Toba didn't just fall on Sumatra, it travelled. The finest particles rode high-altitude winds across enormous distances, and when they settled, they left a thin but detectable layer in sediments across the Indian Ocean, the Bay of Bengal, the Arabian Sea, and deep into the African and Asian continents. Scientists have pulled sediment cores from ocean floors and lake beds thousands of kilometers from Sumatra and found that unmistakable chemical fingerprint, a layer of volcanic glass with the specific geochemical signature of Toba, sitting between other sediment layers that can be independently dated. The dating itself comes primarily from radiometric analysis, specifically argon-argon dating of crystals that formed within the magma and were locked in time by the eruption. These crystals contain radioactive isotopes that decay at known rates, and by measuring the ratio of parent-to-daughter isotopes, scientists can calculate with considerable precision when the crystals were last heated, which is essentially when they erupted. Multiple independent measurements from sites across the world have converged on an age of approximately 73,500 to 74,000 years ago, give or take a few thousand years. But here's where scientists are careful and where you should be too. The estimates for total erupted volume are still debated. Some researchers argue the upper bound of 3,000 cubic kilometers is too generous, that 2,000 is more defensible. Others think we're still underestimating what's buried or eroded beyond detection. The duration of the main eruptive phase is uncertain, possibly days, possibly weeks. And critically, the regional variability in how ash and gases spread depends on atmospheric conditions that we can reconstruct only partially. Some areas almost certainly received far more ash fallout than others, and the difference between a few centimetres of ash and half a metre of ash on the ground is the difference between an ecosystem under stress and an ecosystem that simply stops functioning. What we know for certain is that something extraordinary happened. What we're still working out is exactly how extraordinary, and exactly where the worst of it landed, and that uncertainty matters enormously, because it's the key to the next question. When the ash stopped falling, and the sulfur gases started climbing into the stratosphere, what did they do to the planet's climate? And what was left of the world that humans had been living in? Think about what it means for ash to travel thousands of kilometres and still leave a trace. We're not talking about chunks of rock or visible clouds of debris. We're talking about particles so fine they behave almost like gas, riding the jet stream at altitudes of 30-40 kilometres, suspended for weeks before gravity finally wins, and they drift down onto ocean surfaces and lake beds and ice sheets thousands of miles from where they started. By the time they settle, they're invisible to the naked eye, a thin smear across the sediment, chemically identical to what erupted from Sumatra, but now sitting quietly on the floor of the Arabian Sea, or preserved in a Greenland ice core, waiting 74,000 years for someone with the right instruments to come looking. This is what geologists call tephra, volcanic ash deposited far from its source. And tephra layers are one of the most powerful tools in all of Earth science, because they represent a moment, a single event synchronous across every location where the ash fell. When you find the same tephra layer in a sediment core pulled from the Indian Ocean, and in a cave deposit in southern Africa, and in an ice core from Antarctica, you're not looking at three separate events. You're looking at the same afternoon, or the same month, or the same year, recorded simultaneously in three completely different archives. It's a timestamp that crosses entire hemispheres. The Toba tephra is one of the most widely distributed in the geological record. Scientists have identified it in sediment cores from the Bay of Bengal, where layers of it can be centimetres thick. They've found it in cores from the Arabian Sea. They found it in lake sediments from East Africa. They found traces of it in ice cores from Greenland. Each find adds another data point to a map that shows just how far this eruption reached. And each find also provides another independent location, where the age of the layer can be cross-checked against the surrounding sediment record. But here's where the science gets even more interesting. In many locations, the ash isn't visible at all. You can't see it. You can't find it by looking at a sediment core with your eyes. You find it by dissolving the sediment in acid, removing everything organic, and then searching under high magnification for tiny shards of volcanic glass, some of them only microns across. This is what researchers call cryptotephra, hidden ash. The techniques for finding and identifying it have only been refined in the last few decades, and they've completely transformed our understanding of how far major eruptions spread. Sites that showed no obvious ash layer have been re-examined and found to contain cryptotephra from Toba. The eruption reached places we didn't previously think it had touched, but finding ash is only half the problem. The other half is proving which volcano it came from. Volcanic glass has a chemical fingerprint. The specific ratios of silica, potassium, calcium, iron, and a handful of trace elements are determined by the unique chemistry of the magma that produced it. Every major volcanic system has its own signature, distinct enough that geochemists can match a glass shard found in a sediment core in East Africa to a specific eruption on Sumatra with a high degree of confidence. This matching process, comparing the major and trace element chemistry of unknown tephra against a reference database of known eruptions, is what allows scientists to confidently say that a cryptotephra layer in a cave in India is the same event as the ash deposit sitting on top of Sumatran bedrock. Without that chemical fingerprinting, all you have is a layer of mysterious glass. With it, you have a connection across 5,000 kilometers. What the ash can tell us is remarkable. It can tell us roughly where the heaviest fallout occurred, because thicker and coarser deposits tend to be closer to the source. It can tell us about wind patterns at the time of the eruption, because the distribution of ash traces the direction and strength of atmospheric circulation 74,000 years ago. It can help us date other things found in the same sediment layer, artifacts, bones, pollen records, anything that was buried at the same time as the ash becomes anchored to the same moment in geological time. This is why archaeologists and volcanologists often work together at sites in South Asia and East Africa. Finding the Toba layer in a dig site isn't just interesting geology, it's potentially a precise date for whatever was sitting above or below it. But there's something important the ash cannot tell us, and this is where researchers have to be honest about the limits of the evidence. Ash fallout tells you that material arrived at a location. It does not tell you by itself what conditions were like on the ground when it arrived. A centimetre of ash settled from the atmosphere over weeks tells a very different story than a centimetre of ash that fell in a single day. A layer of ash on an ocean floor tells you almost nothing about whether the surrounding terrestrial ecosystems were overwhelmed or merely stressed. And critically, the thickness of ash at any given location is shaped by countless variables. Prevailing winds that shift over days and weeks, rainfall that washed ash out of the atmosphere before it could travel further, topography that caused it to accumulate in valleys and thin out on ridges. Two sites 200 kilometres apart might show wildly different ash thicknesses, even though they experienced the same eruption. So the tephra record gives us the skeleton of what happened. It confirms the scale and the reach. It provides the timestamps. It traces the trajectory of ash across 3 ocean basins. What it cannot do is tell us what it was like to be alive in the weeks and months after the sky went dark. For that, you need to look at something else entirely. You need to look at what the eruption did to the atmosphere, and through the atmosphere, to the global climate system. Because the ash that crossed oceans was only the first thing Toba sent into the sky. The second thing was worse. Ash is dramatic. It buries landscapes, collapses roofs, chokes lungs. But as far as the global climate is concerned, it's mostly a sideshow. The real danger from an eruption like Toba isn't the ash you can see, it's the gases you can't. When that magma chamber under Sumatra finally tore itself open, it didn't just blast rock into the sky. It released enormous amounts of sulfur-bearing gases, especially sulfur dioxide. Down near the ground, sulfur dioxide is an air pollutant. High in the atmosphere, it becomes something far more consequential. It's the raw material for a planetary sunshade. Here's how that works. Most of the ash from even a giant eruption ends up in the lower atmosphere, the troposphere, the layer where our weather happens. Down there, everything is messy and turbulent. Storms wash particles out. Gravity pulls them down. Rain sticks ash to raindrops and brings it to the surface in days to weeks. That ash can be devastating locally and regionally, but it doesn't stay up long enough to rewire the planet's energy budget. Sulfur dioxide is different. Powerful eruptions like Toba punch a column of gas straight up into the stratosphere, the calmer layer above the weather. Once sulfur dioxide reaches the stratosphere, it starts reacting with water and oxygen to form tiny droplets of sulfuric acid. These are stratospheric aerosols, and they're almost perfectly designed to meddle with sunlight. Each droplet is microscopic, but there are trillions upon trillions of them, forming a thin, hazy veil wrapping around much of the globe. Sunlight hitting this veil is partly reflected back into space before it can warm the surface. Less sunlight reaches the oceans, less reaches forests, savannas, and ice sheets. The planet as a whole starts to cool. This is what scientists mean by a volcanic winter. Not a literal winter with snow everywhere, but a period when the entire Earth system is getting less energy from the sun than usual because of that reflective aerosol blanket in the stratosphere. The chain of events looks something like this. Eruption to sulfur gases into the stratosphere to conversion to sulfuric acid aerosols to more sunlight, reflected to space to surface, cooling to shifts in winds, rainfall and ocean circulation. Each step is reasonably well understood from physics and from observations of more recent eruptions. But when you put them together in the context of something as huge as Toba, the details get complicated very quickly. One way to make this more concrete is to look at eruptions we've actually seen. In April 1815, Mount Tambora in Indonesia erupted with a force that's one of the largest in recorded history, though still smaller than Toba. It injected an estimated tens of millions of tons of sulfur into the stratosphere. Over the next year, global average temperatures dropped by about 0.5 degrees Celsius, maybe a little more. That doesn't sound like much, but climate doesn't need big numbers to cause big problems. In 1816, much of the Northern Hemisphere experienced what came to be called the year without a summer. Frosts in June and July in North America, crop failures and famines in Europe, strange coloured sunsets. People didn't know why at the time, but what they were living through was the downstream effect of a sulphur-rich plume from a volcano in Indonesia rearranging the way sunlight reached Earth. Go back a bit further. In 1783, the Laki Fissure eruption in Iceland spewed sulphur into the atmosphere for months. It caused regional cooling and severe air pollution across Europe. The 1991 eruption of Mount Pinatubo in the Philippines was smaller than both Tambora and Laki, but it still cooled global surface temperatures by around 0.4 to 0.6 degrees Celsius for a couple of years. In each case, the mechanism is the same. Stratospheric aerosols reflect sunlight. The planet cools, rainfall patterns shift. These eruptions give us a laboratory for understanding what sulfur aerosols do to the climate system. They also give us an important caution. Even with historical data and modern satellites, the effects aren't simple or uniform. Some places get colder and wetter, others get colder and drier. Some regions may even get slightly warmer for a time because of how winds and ocean currents reorganize themselves. Now scale that up to something like Toba. Estimates vary, but many researchers think Toba released several times as much sulfur as Tambora, possibly an order of magnitude more. If that sulfur reached the stratosphere as efficiently as we think, it could have created a far denser and more long-lived aerosol layer. In some climate model simulations, a Toba-sized eruption produces global average surface cooling of several degrees Celsius, with the strongest effects in the tropics and mid-latitudes. But here's where we have to be careful. Those model results aren't all the same. Different groups plug slightly different numbers into their simulations. Different assumed sulfur yields, different plume heights, different background climate conditions. Some models produce catastrophic, decade-long cooling. Others show a more moderate temperature drop lasting a few years, followed by a slower recovery. Why the disagreement? Part of the problem is that the climate system is not a simple linear machine. A certain amount of sulfur doesn't always produce a proportionate amount of cooling. The outcome depends on what the climate was already doing at the time, how much ice was on the continents, how warm the oceans were, how strong the monsoon systems happen to be. It also depends on feedbacks. Cool the surface and you can increase snow and ice in some areas, which then reflect even more sunlight, amplifying the cooling. Change temperature gradients between the equator and the poles, and you alter jet streams, storm tracks, and monsoon circulations. Those, in turn, change where clouds form and how much radiation they reflect or trap. A volcanic winter isn't just a big refrigerator switch. It's a nudge to a complex, interconnected network of processes that can respond in unexpected ways. One of the most sensitive pieces of this network is the monsoon system. Monsoons are driven largely by the contrast between how quickly land and ocean heat up. In a typical year, land warms faster than water in spring and early summer. Warm air rises over continents, drawing in moist air from over the ocean. That moist air rises, cools, condenses, and falls as monsoon rain. Billions of people alive today depend on those seasonal winds and rains, and so did our ancestors 74,000 years ago. Now imagine you suddenly dim the sun. If you reduce the amount of sunlight hitting land surfaces more than you reduce the heat content of the deeper ocean, you can weaken that land-sea contrast. In many model simulations, a large volcanic eruption leads to weaker monsoons, less rainfall over South Asia, parts of Africa, and other monsoon-driven regions. For people living in those zones, cooler temperatures might not be the main issue. Failed rains would be. At the same time, other regions could experience the opposite. Cooling can shift the position of the intertropical convergence zone, the band of intense rainfall near the equator, north or south. Areas that were already semi-arid might be pushed into prolonged drought. Other bands could get more frequent storms. Some simulations of Toba-like eruptions produce drying in the Sahel and parts of India, but increased moisture in equatorial East Africa. The pattern is patchy, not uniform. Then there's the ocean. Oceans have an enormous thermal inertia. They warm and cool slowly. When you blanket the planet with a reflective veil, the surface of the ocean cools, but the deeper layers respond much more sluggishly. A colder surface layer can change how easily deep waters mix upward. That affects not just temperature, but also nutrients and carbon dioxide exchange with the atmosphere. Some models suggest that a Toba-scale eruption could temporarily slow aspects of the global overturning circulation, the great conveyor belts that move heat and salt around the world's oceans. A slowdown in one branch of this system could leave heat piled up in some regions and stripped away in others, creating longer-lasting regional anomalies long after the aerosols have thinned out. So how long would the cooling from Toba have lasted? On the level of the stratospheric aerosol veil, we can make a reasonable guess. Sulfuric acid droplets don't last forever. They coagulate, fall out, or are transported into regions where they eventually settle back to the surface. For eruptions we've observed, the main aerosol-driven cooling tends to last 1 to 3 years, maybe up to 5 for the largest historically documented events. For Toba, with vastly more sulfur, some models extend that direct cooling out to a decade or more, gradually waning as the stratosphere clears. But that's only the first chapter. Once you've perturbed sea ice cover, ocean circulation, and vegetation patterns, the system can take much longer to fully relax back to its previous state. Some simulations suggest that secondary effects, like expanded snow cover in certain latitudes or shifts in ocean heat content, might linger for decades, even a century, before the climate fully reverts to its pre-eruption trajectory. Again, not everyone agrees on the magnitude or duration. Some researchers argue that early models overestimated the sulfur yield, or misrepresented how aerosols clump and fall out. More recent studies with better aerosol physics sometimes produce shorter, less dramatic cooling episodes. Others still find strong, prolonged impacts, especially on rainfall rather than temperature alone. What almost everyone agrees on is that the impacts would have been uneven. There was no single Toba climate. There were many Toba climates. For a small band of hunter-gatherers in what's now Ethiopia, the eruption might have meant cooler, drier conditions and several years of poor plant growth, but perhaps still enough refugees around lakes and rivers to scrape by. For groups living on the Indian subcontinent under a weakened monsoon, it might have been much harsher. Repeated crop failures for wild grasses, collapsing herbivore populations, and landscapes scoured by wind where plants couldn't hold the soil. For people near the equatorial coasts, oceanic buffering might have blunted the worst of the temperature drop, even as fish stocks and coastal ecosystems adjusted to abrupt changes in ocean chemistry and productivity. Volcanic winter is not a simple global blanket of misery. It's a reconfiguration of where misery and opportunity appears. From the vantage point of a super-eruption, the climate system becomes a kind of roulette wheel. Some regions are thrust into multi-year drought. Others get new rainfall regimes. Some coastlines become richer in marine life as nutrient patterns shift. Others see fisheries collapse. Over a timescale of decades, those differences determine which human groups can hang on, which are forced to move, and which vanish from the record. And that's the real significance of Toba's volcanic winter. Not that it plunged the entire planet into a uniform deep freeze for centuries. That image is probably too simple. But that it took an already unstable Ice Age climate and gave it a sharp, uneven shove. A shove that left signatures in ice, in ocean mud, and possibly in the genetic and archaeological traces of the humans who lived through it. To see those signatures, you have to look beyond the ash, beyond even the sulfur veil, and into the slow, layered archives that remember every cold snap and rainfall shift. Those archives are buried in places that almost never see the light of day, locked inside polar ice sheets and hidden under kilometers of ocean water, one thin layer at a time. If you want to know what Toba really did to the planet, you can't interview eyewitnesses. You have to interrogate the ice and the mud. Start with the ice. Snow that falls on Antarctica or Greenland doesn't just melt away. In the coldest, driest parts of those ice sheets, it piles up year after year, century after century, getting compressed into glacier ice. Each year's snowfall traps tiny bubbles of air and tiny traces of whatever was floating around in the atmosphere at the time: dust, smoke, sea salt, and crucially, after a big eruption, sulfur. When a volcano blasts sulfur dioxide into the stratosphere, that gas is eventually turned into sulfuric acid droplets. Those droplets don't stay up forever. Over months to a few years, they slowly drift down. Some are scavenged by falling snowflakes in polar regions. The sulfur they contain gets locked into the growing ice sheet as a thin, acidic layer. Drill down through tens or hundreds of thousands of years of accumulation, pull up a cylinder of that ice, and you've got a chronological stack of atmospheric history. Run a chemical analysis, and one of the things you'll measure is sulfate, left over from sulfuric acid. Most years it sits at a low background level. After a major eruption, it jumps, a spike. Plot those sulfate concentrations downcore and you see a forest of spikes. Big, small, global, regional. Tambora is there, Pinatubo is there. Older eruptions, unknown to history, are there too, each marked by a narrow band of elevated sulfur that fell out of the stratosphere and into the snow. So what does Toba look like? Some ice cores show one of the largest sulfate spikes in the last 100,000 years around the right time. The size of that spike tells us the atmosphere was loaded with volcanic sulfur on a scale comparable to, or greater than, the biggest eruptions we've documented historically. In other words, the sulfur veil we talked about in the last section isn't just a theoretical construct, it left a chemical scar in the ice. But ice cores don't just preserve chemistry, they preserve climate signals too. The ratio of heavy to light oxygen isotopes in the ice shifts with temperature. Colder conditions favour one isotopic ratio, warmer conditions another. By measuring those ratios layer by layer, scientists can reconstruct temperature changes over time, at least locally over the ice sheet, and with some work, as a proxy for broader regional conditions. Around the level where that big sulfate spike appears, you can look at the oxygen isotopes and ask, did things suddenly get colder? In some Antarctic cores, there is evidence of a cooling episode around the age of Toba, a slight dip in temperatures, a change in snowfall patterns. Nothing like a plunge into a new full-blown ice age, but an anomaly on top of the already cold conditions of the glacial period. In Greenland the story is murkier, partly because northern hemisphere climate was already jumping between colder and less cold states at that time. Separating a volcanic signal from the background noise of ice age climate swings is not straightforward, and that's where the oceans come in. While ice sheets keep a running log of what's happening in the atmosphere over the poles, the deep sea quietly accumulates its own archive. Every year, a thin sprinkle of particles settles out of the water column onto the seafloor. Shells of microscopic plankton, clay, organic matter, dust. Over tens of thousands of years, that slow drizzle builds up into thick blankets of sediment. Lower a coring device into the deep ocean, punch it into the seafloor, pull it back up, and you've got a stratified tube of ancient mud. Slice it, date it, analyze it, and you can read a story about temperature, productivity, and circulation at that spot in the ocean. How do you get temperature from mud? Many marine microorganisms build shells out of calcium carbonate or silica. The chemistry of those shells, especially the ratios of oxygen isotopes and certain trace elements, depends on the temperature of the water they grow in. Warmer water, one pattern; colder water, another. Those shells then die, sink, and get buried. By picking them out of different layers in a core and measuring their isotopes, you can reconstruct how sea surface temperatures change through time. Other proxies tell you about productivity. How many of these organisms were living and dying at the surface? How much organic carbon was raining down? Whether the upper ocean was a blooming garden or a relative desert. Look at cores from the Indian Ocean and nearby seas that capture the interval around 74,000 years ago, and some of them show what you'd expect after a major eruption, a brief cooling of surface waters, followed by a recovery. In certain locations, you also see a drop in biological productivity. Fewer plankton shells per unit time, changes in the types of species present. That suggests the surface ocean environment changed enough to stress the base of the marine food web, at least regionally and at least temporarily. In other places, including parts of the Arabian Sea and equatorial Indian Ocean, the records look different. Some cores show stronger signals linked to natural shifts in monsoon strength than to any discrete volcanic event. Some show modest cooling but no obvious collapse in productivity. Again, the impact looks patchy. There wasn't one simple Toba ocean response. Now stitch ice and ocean together, and you hit a technical problem that might sound boring but matters immensely. Dating. Ice cores have their own internal clocks. In some sections, you can count annual layers like tree rings. In others, you rely on models of ice flow and accumulation rates, anchored by known time markers such as spikes from well-dated eruptions or abrupt climate jumps we see in multiple records. Marine sediments are trickier. You might date certain layers with radiocarbon, but that method only works reliably back to about 50,000 years ago. Beyond that, you have to lean on other tools. The decay of different isotopes, the known timing of magnetic field reversals or wiggles, correlations with global sea level changes, or tuning the sediment record to cyclic variations in Earth's orbit that affect climate. Each archive has its uncertainties. When you say, this sulfate spike in Antarctica is 74,000 years old, and this cooling in the Indian Ocean core is 74,000 years old, there's always an error bar, maybe plus or minus 1,000 years, maybe more. To link those signals confidently, you need them to overlap within those uncertainties and ideally be tied to an independent time marker, like a layer of Toba ash found in the same core you're using for climate reconstruction. Sometimes you get that smoking gun, volcanic glass shards from Toba, chemically fingerprinted, sitting in a marine core at a particular depth. Just beneath or just above that ash, you see a change in temperature proxies or productivity. That gives you high confidence that you're looking at the ocean's response to Toba itself, not just some random wiggle. Other times, the match is fuzzier. A cooling event in one record might line up with Toba within the error bars, but so might another climate oscillation or another eruption. That uncertainty is one reason why estimates of Toba's climatic impact still vary. Some researchers argue the ice and ocean records show a short, sharp event, years to a decade of unusual cooling and hydroclimate shifts, then a return to the previous glacial conditions. Others see hints of a longer-lived disruption layered on top of pre-existing trends. So what can we say with reasonable confidence? Most specialists would agree on a few broad points. First, Toba did inject a lot of sulfur into the atmosphere. The polar sulfate spikes are too big to brush aside. This was a major stratospheric aerosol event. Second, there were real measurable climate anomalies roughly in phase with the eruption. Some regions cooled, some monsoon systems appear to have weakened, ocean surface conditions shifted, productivity changed in certain basins. The planet didn't just shrug this off in a year. Third, the effects were not globally uniform or apocalyptic in the sense of a complete, centuries-long deep freeze. The Ice Age world before Toba was already cold. After Toba, it was still an Ice Age world. The eruption added a sharp disturbance, but it didn't single-handedly trigger a brand new glacial maximum or permanently derail the climate system. Where the debate heats up is over the magnitude and duration of that disturbance. Some reconstructions and climate models argue for significant global cooling of several degrees lasting a decade or longer, with knock-on effect stretching over many decades. Others, using different assumptions or focusing on different data sets, see more modest, regionally variable cooling more in line with a scaled-up version of Tambora or Pinatubo, intense but relatively transient. Even more controversial is the link between those physical climate changes and what happened to living things, especially humans. It's one thing to show that a patch of the Indian Ocean surface cooled by a couple of degrees and primary productivity dipped for a few years. It's another to argue that those changes translated directly into continent-wide megafaunal extinctions or a near-total collapse of human populations. This is where a trap appears. It's very tempting to look at a big sulfur spike in ice, a cooling signal in ocean mud, and then jump straight to, therefore, humans almost went extinct. The narrative symmetry is appealing. Giant eruption, dramatic climate event, human bottleneck, all the pieces line up if you squint. But climate signals are not people. A 2-degree regional cooling might be disastrous for crops in an agricultural society that depends on fine-tuned seasonal cycles. For scattered bands of hunter-gatherers used to living in marginal environments, the same temperature drop might be tough but survivable, especially if they can move, switch prey, or exploit refuges. Likewise, a weakening of the South Asian monsoon that shows up clearly in marine cores could mean multi-year droughts on some landscapes, and boom years in others, where rainfall patterns are rearranged, not simply reduced. To understand whether Toba nearly wiped us out, you can't stop at sulfate spikes and isotope ratios. You need to bring in other lines of evidence, archaeological sites that track human presence or absence through the relevant period, genetic data that reflects population sizes, fossil records of animals and plants that shared those ecosystems. The ice and the ocean mud tell us that Toba was a genuine planetary event. They show us that the world our ancestors inhabited did, in fact, flicker and wobble in the wake of that eruption. But they don't, by themselves, tell us how many people died, how many survived, or where. For that, we have to move from frozen archives and seafloor sediments back onto the continents, especially to the regions that sat almost directly downwind of Toba when the ash and aerosols spread. Places like South Asia, where the climate roulette wheel may have landed on some of its harshest outcomes. If you look at a map, the bullseye is obvious. Toba sits on the island of Sumatra, right along the equator. To its northwest lies the Bay of Bengal. Keep going, and you hit the Indian subcontinent. First the Andaman and Nicobar Islands, then the eastern coast of India, then, farther inland, the Ganges Plain and the heart of South Asia. Eruptions on this scale don't just throw ash straight up. They interact with real winds in a real atmosphere. At the time of Toba, the dominant circulation in this region would have included strong equatorial easterlies and monsoon systems that seasonally pump air north and west. That means a colossal umbrella of ash and aerosols could have been steered over the Indian Ocean, across the Bay of Bengal, and straight onto the Indian subcontinent. And we're not talking about a light dusting. Closer to the volcano, Sumatra itself, the Andamans, parts of the eastern Indian Ocean, ash would have fallen thick and fast. Think tens of centimetres or more in some areas, maybe metres in the zones closest to the source. Even as the clouds stretched out and thinned, it could still drop enough fine material over India to smother landscapes, clog river systems, and leave a geologic calling card we can dig up today. When that much ash hits the ground, the problems start immediately. First, water. Volcanic ash is not like fireplace soot. It's pulverized rock, tiny shards of glass and crystals. When it lands on lakes, ponds, or rivers, it can turn clear water into a dense, abrasive slurry. The smallest particles stay suspended for a long time, making the water cloudy and potentially toxic. Dissolved components can change pH and chemistry. Animals that drink from those sources can get sick or die. Humans, depending on shallow pools and slow-moving streams, suddenly find their water supply compromised. Second, plants and whatever you're eating. In a farming society, heavy ashfall means crop failure. Leaves get coated, photosynthesis drops, stems snap under the weight. Roots suffocate if ash forms an impermeable cap on the soil. At Toba's time, nobody was farming yet in South Asia. People were foragers, hunters, fishers. But they still relied on plant communities that could be hammered by ash. Fruit-bearing trees, shrubs with edible tubers, grasses whose seeds could be collected, all could be damaged or killed outright. Ash can also change the ground itself. A layer a few centimetres thick can seal the surface, slowing infiltration of water, leading to more runoff and erosion. Seeds have trouble sprouting through it. Buried root systems might rot. Over years to decades, weathering can eventually turn ash into fertile soils, but in the short term, it's a shock to the system. Third, air. Fine ash is brutal on lungs. Inhaled particles can lodge deep in the respiratory tract, causing coughing, inflammation, and long-term damage. For people already stressed by cold, food shortages, or disease, that extra insult can be the difference between life and death. Grazing animals, already scraping by in Ice Age ecosystems, would have faced the same problem. Kill enough herbivores through respiratory distress and starvation, and predators, human and non-human alike, lose critical food sources. Fourth, light. Even if you're not under the thickest part of the plume, a sky hazed by ash and sulfuric aerosols cuts down the sunlight reaching the surface. Days become dim, colours muted. Photosynthesis slows, temperatures drop, especially at night. For humans, this means colder, darker seasons, tricky hunting conditions, and disorienting changes in familiar landmarks. For ecosystems, it means stress layered onto an already glacial world. So, if you were a group of early humans living somewhere in what's now India when Toba went off, your problems might have arrived from the sky. The question is, were they there? And if they were, can we see what happened to them in the ground beneath our feet? Archaeologists have been chasing that question in a handful of key regions across South Asia. Think of these as windows cut into different parts of the landscape that lay downwind of Toba's ash cloud. One of the most famous windows is the Jwalapuram region in southern India, particularly a site called Jwalapuram Locality 3 in what is now Andhra Pradesh. Here, researchers found stone tools, flakes and points made in a style broadly similar to what we call Middle Paleolithic technologies, both below and above a distinctive layer of volcanic ash. Chemical analysis of glass shards in that ash links it convincingly to Toba. It's not just some local eruption, it's the global giant we've been talking about. Below the ash, you have a sequence of stone artifacts made by humans or human relatives. Then comes the ash layer, up to several tens of centimetres thick in some exposures. Above it, after a gap of time, there are more stone tools. And here's the important part. The tools above and below look in many respects like they're part of the same technological tradition. Same general methods of flaking, same overall shapes and sizes of points and scrapers, same preference for certain raw materials. If you laid them all out on a table without labels, you'd have a hard time telling which ones came from pre-Toba horizons and which from post-Toba ones. To one school of thought, that continuity is a powerful argument. It suggests that whatever Toba did to the climate and the landscape in this region, it did not completely wipe out the human groups who were living there. Their way of making tools, their learned cultural tradition, survived across the ash line. That implies some degree of demographic continuity. People living through the event, adapting and carrying on. Jwalapuram isn't the only place where Toba ash and stone tools intersect. Farther north and west, in parts of the Narmada and Sun River systems, researchers have identified buried surfaces with Middle Paleolithic tools and, in some cases, overlying or nearby ash layers thought to derive from Toba. In the Jureru Valley, in the same broad region as Jwalapuram, other localities also show similar patterns. Human-made artifacts, then ash, then more artifacts. On the other side of the Bay of Bengal in the Andaman Islands, Toba ash appears in marine and coastal deposits, marking another part of the fallout footprint. And in marine cores off the Indian coast, that fine glassy dust has been traced tens to hundreds of kilometres from land, telling us the ash cloud passed overhead. Put all this together, and South Asia looks less like a blank zone of annihilation, and more like an area that was heavily hit, but still inhabited before and after. But the story is not that simple. For one thing, our windows are tiny. Most of India's surface doesn't preserve 74,000-year-old landscapes in a way that's accessible. Rivers cut, sediments erode, soils form and reform. Sites like Jwalapuram are rare, partly because the right combination of deposition and preservation happen to lock in a sequence that spans the critical interval. That means absences in the archaeological record can mean two very different things. They might mean there was nobody there, true demographic collapse, people dying or abandoning the region. Or they might mean that people were there, but the specific layers holding their traces have been eroded away, buried too deep, or simply not yet found and excavated. This is the gap problem. Look at a sequence and you'll almost always see breaks, intervals where no artifacts are preserved. The temptation is to fill those gaps with stories. But the rock record is biased. Catastrophic events, like a thick ashfall, may actually have a better chance of being preserved than quieter times. So what do archaeologists see when they look closely at South Asia across the Toba horizon? Some argue strongly for continuity. They point to the similarities in tool technology, the lack of a clear before and after shift, and the presence of human occupation layers immediately above the ash at some sites. In this view, Toba was a major environmental disturbance, but local human groups in at least parts of India weathered it, perhaps by moving within the region, exploiting refugia, and leaning on flexible subsistence strategies. Others are more cautious. They note that even at Jwalapuram, there seems to be a hiatus between the ash deposition and the resumption of artifact accumulation. That gap could represent decades, centuries, or longer, during which local populations were reduced, displaced, or absent. The tools above the ash, though similar, might belong to recolonizing groups that arrived after conditions improved, carrying broadly similar technology from elsewhere. Still others highlight regions where we see rich Middle Paleolithic occupations before Toba, but no clear post-ash signal in the immediate vicinity. Is that because people disappeared from those specific landscapes, or because post-Toba sediments were never deposited or later got washed away? Both possibilities are on the table. There's also the issue of scale. Continuity at one valley-scale site doesn't tell you what happened across all of South Asia. It's entirely possible that some pockets, sheltered river valleys, coastal zones with buffered microclimates, areas with resilient groundwater-fed springs, served as refuges where people could hang on. Other regions, drier or more directly buried under thick ash, might have seen local extinctions or long-term abandonment. When you zoom out, three broad interpretations compete. 1. Strong continuity. Humans were widespread in South Asia before Toba, took a hit but remained present during and after, and their basic cultural traditions persisted with relatively little disruption. 2. Major disruption. The eruption caused such severe environmental stress that large parts of the subcontinent were depopulated for a time. Later populations, perhaps coming from surviving groups in more favourable regions, recolonized and re-established tool-making traditions that look similar but reflect a demographic break. 3. Apparent gaps are mostly about preservation. The real demographic story was noisy and spatially complex. Local crashes here, stability there. But our fragmentary record exaggerates the emptiness and sharpness of those changes. Right now, no single interpretation has crushed the others. New sites, better dating and more refined analysis of tool assemblages keep nudging the debate in different directions. But one lesson is already clear. South Asia was not some distant, untouched observer of Toba's fury. It sat practically under the fallout plume, took huge doses of ash, and yet still preserves traces of human life that bracket the event. Those traces don't look like the aftermath of a total wipeout. They look like the signature of resilience under pressure. Stress, disruption, movement, and survival. Which brings us to the uncomfortable question. If people were in India before Toba, and some were thereafter, did the eruption actually erase entire populations in that region? Or is the story of a human winter over South Asia more myth than reality? So let's take that question head on. Did humans actually vanish from India after Toba, leaving an empty, ash-choked landscape to be repopulated only much later? Or did some groups somehow ride out the chaos, clinging to scattered refugees until the skies began to clear? Archaeologists usually frame this as a debate between two big ideas. On one side, there's what you might call the catastrophe hypothesis. In this view, Toba was not just a bad day for the neighbours, it was a regional reset button. Thick ash, poisoned water, dead plants, collapsing animal populations, colder temperatures, all stacked together to push human groups in South Asia past their breaking point. Local populations die off. Foragers already living close to the edge suddenly find that the patch they know, the river bend, the hunting ground, the grove of edible plants, can no longer support them. Maybe they try to move, following rivers downstream, heading toward coastlines, seeking fresher water and surviving vegetation. But they're not the only ones. Other stressed groups are on the move too. Encounters can turn violent. Disease spreads in crowded refuges. Starvation stalks the margins. Under this scenario, huge swaths of the subcontinent could have been emptied of people. Not forever, but for long enough that the original residents left no direct descendants in those exact landscapes. What you see above the ash in this picture is recolonization. The first stone tools that show up after the eruption aren't made by the same bands who were living there before. They're made by their cousins, survivors who held on somewhere else, maybe in wetter refuges at the southern tip of India, maybe along the Arabian coast, maybe even farther afield. When conditions stabilized enough, ash weathered into soil, plants regrew, animal herds returned, these survivors pushed back into the empty territories. From a distance, this can look like continuity. Middle Paleolithic tools before Toba, Middle Paleolithic tools after Toba. Same general shapes, same basic methods of flaking. But in the catastrophe model, that's a cultural echo, not an unbroken local lineage. The tradition survived in people who never left their refuges. Later they repopulated the vacuum. On the other side is the continuity hypothesis. In this story, Toba was a hammer blow, but not a clean slate. Human groups in South Asia were hit hard, absolutely, but some of them stayed put or shifted only short distances. They suffered losses, abandoned the most heavily ash-buried patches, maybe retreated into nearby hills, caves, and river canyons where water stayed clearer and vegetation could hang on. They shrank, rearranged their territories, changed their seasonal movements, but they didn't disappear. From this perspective, the similarity of stone tools across the ash line at places like Jwalapuram isn't just coincidence, it's the fingerprint of real demographic survival. The same learning chains, the same "this is how we make a point, this is how we sharpen a scraper" knowledge, transmitted through parents and elders, bridged the eruption. The people above the ash are literally the descendants of those below it. But here's where it gets messy. Both sides lean heavily on stone tools. Because that's mostly what we have. At 74,000 years ago in South Asia, we don't have skeletons we can sequence for DNA across the Toba boundary. We don't have preserved campsites full of organic remains. We have lithics, flakes, cores, points, scrapers. Which brings us to an uncomfortable reality about Paleolithic archaeology. Stone tools are a terrible way to track specific populations. They're good at telling you that humans, or at least someone with human-like hands and brains, were present in a given layer. They're good at showing broad technological traditions, simple versus complex flaking, prepared cores versus casual chipping, presence or absence of certain projectile point types. But they're not great at telling you whether the group making them is the exact same biological population, in the genetic sense, as the one that was there 1,000 years earlier. Imagine trying to reconstruct modern migration patterns 100,000 years from now if the only thing you had was a layer of iPhones and a layer of slightly newer smartphones above it. Same general technology, same basic design logic. Did the people in the city die and get replaced by newcomers from another continent who happened to use similar phones? Or did the same population just upgrade their devices? The objects alone won't settle that. It's similar with Middle Paleolithic tools. Two different groups, separated by hundreds of miles, can independently develop very similar flaking strategies just because they're working with the same raw materials and facing the same functional problems. Meanwhile, the same group over 1,000 years might tweak details of their toolkit without changing the overall style enough for us to notice. So when we see continuity in stone tools across Toba ash in one valley, we have to be careful. It might mean continuous local occupation. It might mean a temporary vacant landscape later recolonized by people with closely related cultural traditions. It might even mean that two different populations, separated in time, converged on similar technological solutions because those solutions just work well with that kind of stone. Now add another complication, site abandonment. When archaeologists see that a particular locality has tools before Toba, then ash, then nothing afterward, There's a temptation to tell a dramatic story. Everyone died. The place became uninhabitable. Silence falls over the valley. But abandonment can mean many things. It can mean death, yes. A group overwhelmed by ashfall and climate stress, gone for good. It can also mean migration. People leaving a devastated patch and moving to more favourable zones just over the horizon. Maybe they switch from inland river valleys to the coast, exploiting shellfish and marine resources. Maybe they move upslope into foothills, tracking springs and seepages less affected by ash. Those new habitats might not preserve their traces in the same way. Coastal lands that were dry 74,000 years ago could now be underwater due to sea level rise. Upland camps on thin soils could have been eroded away. Rock shelters might hold the record of these moves, but we haven't found or excavated the right ones yet. Our current sites are a biased sample of a much larger behavioural landscape. So a gap in one valley's archaeological record might not be a true human absence. It might simply be a shift into zones that, by bad luck, don't show up in our data. The reverse is true too. Places that look continuous, pre-ash tools, ash, post-ash tools, might hide real demographic chaos inside what looks like a clean sequence. Maybe there was a break of several centuries where nobody lived there, followed by recolonization. Our dating methods, with their uncertainties, might blur that hiatus into what looks like a smooth story. This is why the catastrophe versus continuity debate is still very much alive. Both sides can point to the same limited evidence and pull out different narratives. The catastrophe camp emphasizes site hiatuses, sharp drops in artifact density, and the sheer scale of environmental disruption implied by the ash and climate models. The continuity camp emphasizes technological similarity, the presence of occupation right above the ash in some places, and the resilience we see in forager societies in other tough environments. Underneath that, there's a growing recognition that the real answer probably lies somewhere in between. Local extinctions almost certainly happened. You don't drop tens of centimetres of ash on already stressed Pleistocene ecosystems without wiping out some bands entirely. Small, isolated groups could have been erased with no survivors to tell their story. But total regional extinction is a much higher bar. For that, you'd need every refuge to fail at once, every spring to clog, every patch of less buried forest to die, every cave and sheltered valley to starve. You'd need unlucky timing, where multiple years of hardest impact hit before migrations could connect survivors. You'd need a disaster footprint bigger, in effect, than the diversity of microhabitats across the entire subcontinent. Most researchers today lean toward a patchwork picture. Some regions of India may have been abandoned for centuries or longer. Others likely hosted reduced fragmented populations, remnant groups exploiting whatever niches remained viable. Over time, as ash weathered and climate stabilized, those survivors' descendants, along with arrivals from neighboring areas, spread out to refill the empty spaces, and as we're trying to sort that out, the ground itself keeps changing the conversation. New finds have a habit of blowing up neat stories. For years, Jwalapuram was held up as the key to post-Toba continuity in India. Then other sites began to complicate the picture, some with evidence of disruption, some with different tool traditions, some with awkward dates that didn't fit early models. Better dating of the ash itself narrowed the eruption window. More refined analyses of stone tools revealed variation that earlier, coarser studies had missed. In some cases, layers once thought to be sterile turned out, under more careful excavation or improved techniques, to hold tiny fragments of human activity. In others, deposits confidently assigned to Toba were reinterpreted as belonging to different eruptions, forcing rethinks of supposed cause and effect. Each new trench, each new core, has the potential to overturn whatever we thought we knew last decade. That's the real answer to did humans disappear from India? We don't fully know because the record is fragmentary, biased, and still being written. What we can say is that the subcontinent was hit hard, that some landscapes were probably emptied, that others likely served as refuges, and that at least some human cultural traditions either persisted in place or were quickly reintroduced after the skies began to clear. And we can say one more thing. However bad it was in India, the story of Toba doesn't stop there. The real shockwaves show up not just in ash and stone, but in our DNA, and in an idea that once gripped the scientific imagination, that this single eruption nearly wiped out our entire species. To see whether that claim holds up, we have to leave the river valleys of South Asia and dive into the genomes of people alive today. When geneticists first started sequencing human DNA at scale, they noticed something strange. For a species with billions of individuals and a global range, we're oddly uniform. Chimpanzees living in a single forest in Central Africa can have more genetic variability than humans spread from the Amazon to Australia. Put two random chimps side by side, and on average, they'll be more different genetically than two random humans from opposite ends of the Earth. That's a clue. Not about the present, but about the past. In population genetics, there's a concept called a bottleneck. Imagine you have a big jar full of marbles in every colour. That's a large genetically diverse population. Now pour those marbles through the neck of a bottle so only a few can squeeze through. Whatever comes out the other side is still a mix of colours, but some are missing, and the overall variety is much lower. That's what a population bottleneck is, a drastic temporary reduction in the number of breeding individuals. Most lineages die out. A tiny fraction make it through and become the ancestors of everyone who comes later. Genetically, that kind of event leaves scars. You get patterns like reduced overall diversity, long stretches of DNA that are unusually similar between people, and an overrepresentation of certain mutations that just happen to be in the lucky survivors. With the right models, you can work backwards from those patterns and estimate how big the ancestral population was at different times. And as those models got better in the 1990s and early 2000s, a story began to emerge. Many analyses suggested that sometime in the Middle Pleistocene, our lineage had gone through a severe squeeze. Not a mild trimming, not a slight dip, something that took what had been a widespread, numerous population and crushed it down to a few thousand breeding individuals, maybe fewer. You could phrase it like this: almost everyone died, at least in genetic terms. The timing estimates were blurry, but a lot of early work pointed to a window between roughly 100,000 and 200,000 years ago. Then Toba stormed back into the conversation, because here was a perfect villain, a real physical catastrophe we could point to, a single eruption big enough to throw climate into chaos, blanket huge regions with ash and hammer ecosystems from India to East Africa, a giant smoking gun dated to about 74,000 years ago. It didn't take long for someone to draw a connecting line. What if Toba didn't just devastate South Asia? What if its global climatic fallout was so extreme that it crashed human numbers worldwide? What if that genetic bottleneck the models were picking up was the echo of this one event? The idea was electrifying. In this picture, there might have been tens or hundreds of thousands of our ancestors scattered across Africa and Eurasia before the eruption. Then Toba goes off. Sunlight drops. Plants die back. Animal populations crater. Human groups already living lean get pushed over the edge. Band after band blinks out. The only ones who make it through are a few scattered refugial populations. Maybe some in East Africa near reliable lakes. Some along coasts where marine food webs are buffered. Maybe a handful in sheltered river systems less affected by ash and drought. Different researchers offered slightly different numbers, but the core claim was stark. Humanity might have been reduced to just a few thousand breeding individuals. Sometimes you'd see popular accounts boil it down even further. Only 2,000 people, maybe as few as 1,000 couples. Suddenly the Toba super-eruption wasn't just a geological curiosity. It was recast as the near-death experience that shaped every human alive today. A single bad year, or really a bad millennium, where our entire species almost disappeared. It's the kind of story our brains love. Simple cause, dramatic effect. One catastrophe, one bottleneck, one narrow escape that explains both our low diversity and our shared ancestry. From a narrative point of view, it's perfect. From a population genetics point of view, it's messier. To see why, you have to look at how these bottleneck inferences actually work. When geneticists say the human population dropped to a few thousand, They're usually talking about something called effective population size. That's not a literal census count. It's not the number of faces you'd see if you could time travel and line everyone up. Effective population size is more like the number of individuals who are contributing genes in a way that matters to long-term evolution. Imagine two populations with the same head count, 10,000 people each. In one, everyone has roughly equal chances to mate and have children. In the other, a tiny elite have lots of offspring, and most people have none. Genetically, those two populations behave very differently. The second one will lose diversity faster. Random genetic drift will be stronger. The gene pool will be dominated by a few lineages. From the DNA's perspective, that skewed population behaves as if it were much smaller than it really is. That's effective size. It's also influenced by how populations are structured and how they change over time. If your ancestors were arranged in small, semi-isolated bands that occasionally exchange mates, with some groups flickering out and others expanding, the genetic signal can look like a world of just a few thousand effectively breeding individuals, even if the actual census size was significantly higher. So when early studies said, we see a bottleneck down to 2,000 to 10,000 humans, that didn't necessarily mean there were only that many living individuals huddled in caves around the world. It meant that, from the viewpoint of the genes that made it to the present, the ancestral population behaved as if it were that small. Now fold in another complication: time resolution. Genetic data are great at capturing broad trends, periods when diversity shrank, when certain lineages expanded, when populations split or merged. But they're not time-stamped the way a volcanic ash layer is. Every time you estimate the timing of a demographic event from DNA, you're stacking assumptions. You assume a mutation rate, how often new changes appear in the genome. You assume a generation time, how many years on average between parent and offspring. You assume a model of how populations related to one another. Were they isolated, continuously mixing, periodically exchanging migrants? Change any of those and your clock shifts. A bottleneck that looks like it happened 70,000 years ago under one set of assumptions might move to 100,000 years ago, or 150,000 years ago under another. Stretch or compress the timescale enough, and the overlap with Toba starts to look more like a coincidence than a clean cause and effect. On top of that, the signal you see in genomes is usually smeared over thousands or tens of thousands of years. It's not like reading a seismograph for a single earthquake. It's more like looking at a long blurred line and trying to decide exactly when someone started pushing the pen. So when people said, look, humans have low diversity, the models show a bottleneck, Toba happened around the same time, case closed, other researchers pushed back. Were we really seeing the fingerprint of one catastrophic eruption? Or the cumulative effect of a long drawn-out period of climate instability, habitat fragmentation, and shifting population structure that played out over hundreds of thousands of years? As more data came in, from more parts of the genome, from more individuals around the world, the neat story started to fray. Some analyses pushed the most severe bottlenecks farther back in time than Toba, into earlier glacial cycles and older climate crises. Others suggested that the few thousand ancestors might never have been a single, tightly clustered group, but rather a set of interconnected subpopulations spread over a wide area, exchanging mates just enough to behave, in aggregate, like one smallish metapopulation. There were still deep troughs in effective population size, but pinning those troughs to one eruption 74,000 years ago became a lot harder. So where does that leave the Toba bottleneck idea today? Most researchers agree on a few broad points. Humanity has gone through demographic squeezes. Our genetic uniformity is not an illusion. At various times in the Pleistocene, our effective population size really did fall to levels where a few thousand breeding individuals were carrying the torch for our entire lineage. It's also hard to deny that Toba was a massive eruption with serious regional impacts. It almost certainly made life much harder in some parts of the world, and it may well have contributed to local population crashes or extinctions. What's debated is the leap from big volcanic disaster to near global human extinction. Did Toba trigger the most severe bottleneck in our history? Or did it land on a species that was already small and patchy for other reasons? Was its demographic impact global and synchronized, or regional and staggered? Are the dips we see in genetic reconstructions aligned with Toba by cause, or just by rough coincidence in a noisy, low-resolution record? Those are still open questions. The current trend in the field is cautious. genetic evidence does support the idea that our ancestors went through tough, low-diversity phases. Bottlenecks happened. But tying those bottlenecks tightly and uniquely to Toba, as if one eruption almost single-handedly shaped the human gene pool, is no longer the mainstream view. Instead, the picture looks more like this: a long history of climatic swings, habitat shifts, and ecological stresses repeatedly pushed hominin populations into vulnerable states. Toba was one brutal chapter in that story, possibly a major one, but not necessarily the sole author of our genetic narrowness. To get beyond speculation, we need to line up three independent records: the geological story of the eruption, the archaeological story of who was living where and doing what, and the genetic story of how many ancestors we have and when their lineages expanded or contracted. We've looked at the ash and the tools. Next, we have to dive deeper into the DNA itself and see what it really says about how close we came to vanishing and whether Toba deserves its reputation as the volcano that almost erased us. So, what happens when you actually do that? When you take all the new DNA we've collected, throw the latest math at it and ask, okay, how many of us were really left, and when? The story gets less cinematic but more interesting. For one thing, the datasets have exploded. Those early bottleneck studies were often based on a handful of genetic markers, maybe from a few dozen or a few hundred people. Today, we're talking about whole genomes from tens of thousands of individuals worldwide, plus ancient DNA from Neanderthals, Denisovans, and early Homo sapiens. And the methods have grown up too. Instead of simple curves of population size through time, researchers now use approaches that can model multiple populations at once, allow for migration between them, and fit very complex histories: splits, merges, expansions, crashes, all at the same time. When you run those newer models, you still see bottlenecks. You still see long periods where effective population size is low. But the exact timing, depth, and shape of those squeezes look different than the clean dramatic valley people used to draw on the whiteboard. In some reconstructions, the most dramatic contraction in our lineage isn't a sharp dip around 74,000 years ago. It's a long, drawn-out low point stretching from roughly 900,000 years ago into the mid-Pleistocene, a period when global climate was changing in big ways and many mammal species were under stress. Other studies, focusing on more recent times and different parts of the genome, do see a reduction in effective size somewhere between roughly 100,000 and 50,000 years ago, but not always as a single, synchronized cliff. Sometimes it looks more like a series of steps. Population small, then smaller, then a bit bigger, then smaller again. The key shift is this. Instead of one clean, sudden Toba bottleneck, the genetic record is starting to look like a landscape of hills and valleys shaped by many forces. Long-term climate swings, glacial cycles, drying and greening of key habitats, the expansion and contraction of deserts and forests, periods when different human groups were isolated then reconnected, waves of migration where one group grew rapidly while another faded. In that kind of world, you don't need one super-eruption to explain a low effective population size. You can get there just fine with a few 100,000 years of being a small, scattered, vulnerable species living through repeated climate chaos. This brings us to an important point. What else, besides a volcano, can drive a bottleneck signal in DNA? One obvious candidate is simple climate instability. Over the last million years, Earth's climate has been flipping between colder and warmer phases on a roughly 100,000-year rhythm. Ice sheets grow, sea levels fall, rainfall belts shift. Then it all swings back. Each transition reshapes habitats. Grasslands turn to desert, forests retreat, coastlines move, animals migrate or die out. If you're a species that depends on certain prey, certain plants, certain routes between water sources, those swings can be brutal. Your range shrinks. Populations get stuck in isolated refuges. Some lineages die out entirely, others hang on in pockets. From the perspective of your genes, that repeated expansion and contraction can look a lot like a bottleneck. Fewer breeding individuals, more drift, more loss of diversity. Another driver is migration itself. Think about what happens when a small group leaves a larger population and colonizes a new region. That founder group only carries a subset of the genetic variation from back home. Even if they do well and their numbers explode, they're expanding from a narrowed gene pool. Geneticists see this pattern in our out-of-Africa history. Modern non-African populations tend to have less genetic diversity than African populations. That's consistent with a founder effect. A relatively small group leaving Africa maybe 50 to 70,000 years ago, then expanding across Eurasia and beyond. If you don't account for that structure, if you just lump everyone together and pretend the whole species was one random mating blob, you can misread those founder events and regional expansions as a single global bottleneck. Which leads to a third factor: population structure. Remember those scattered bands, those metapopulations from earlier in the story? That's not just a thought experiment. It's how humans, and many animals, actually live. You have clusters of groups connected by mating and trade locally, but only occasionally exchanging members with distant clusters. Some clusters do well, others crash, some merge, some fragment. Over time, that produces a genetic pattern where, even if the total number of humans is decent, the effective population size looks small, because genes aren't being shuffled efficiently across the whole species. A few subpopulations end up contributing disproportionately to the future. Others leave no descendants. From the long-term, genome-wide perspective, it can look as if only a few thousand individuals ever mattered, genetically, even if the head count was much higher and more spread out at any given moment. This is crucial when we bring Toba back into the picture. You can imagine a world where regional populations around the Indian Ocean get hammered by ash, drought, and ecosystem collapse. Other populations, in parts of Africa or maybe Far East Asia, are affected but not annihilated. Their numbers dip, then recover. The species as a whole stays small and patchy, not because literally everyone almost died on the same day, but because the global environment over tens of thousands of years kept us from ever becoming truly abundant. In that scenario, you absolutely can have severe global genetic narrowing coexisting with regional survival. A group in southern Africa might ride out Toba in relative safety. Another along an East African coast might do the same. Their descendants, thousands of years later, expand and eventually contribute most of the genes that show up in modern humans. Meanwhile, groups closer to Toba's ground zero blink out completely, leaving no direct genetic trace. From the standpoint of present-day DNA, it still looks like only a few thousand effective ancestors. But that doesn't necessarily mean only a few thousand terrified people hiding in the same cave, or even alive on Earth at one particular moment. It could mean that, across space and time, only a small fraction of the many humans who lived back then ended up contributing to the future. This nuance is where the only 1,000 survived line starts to wobble. You still hear it a lot, in documentaries, in popular science books, in clicky headlines. It's a powerful phrase. It makes our existence feel fragile, miraculous. But in current research, that claim is better treated as one possibility, not a resolved fact. There are still models that, under certain assumptions, produce very small effective population sizes in the late Pleistocene. Some scientists think those models really do reflect a near species-wide crash, perhaps with Toba playing a role, perhaps not. Others argue that once you add more realistic structure, migration, and long-term climate noise, you don't need a single, hyper-severe bottleneck to explain what we see. You just need a chronically low, spatially patchy population riding out repeated environmental shocks, and a growing number of studies point to major demographic events that clearly predate Toba. One recent line of work even suggests a deep, prolonged bottleneck around 900,000 years ago that might have cut our ancestral population down to just a few hundred breeding individuals for many millennia, long before our own species existed, and long before any Toba-sized eruption we know of. If that's right, then the near extinction that most profoundly shaped our genomes might have happened in a world with no Homo sapiens, no Toba, and a very different set of climatic and ecological pressures. So rather than one near death, our lineage may have survived several. Where does this leave the volcanic apocalypse narrative? It doesn't kill it outright, it just blunts its edges. It's still possible that Toba caused a serious demographic downturn, perhaps especially in South Asia and along some migration corridors out of Africa. It's possible that this downturn coincided with, and amplified, an already stressed global population, and that the combined effect shows up as one of the dips in our reconstructed effective size. But if you ask, is there a clear, unambiguous genetic signature that screams Toba almost wiped us out worldwide? The answer from most geneticists today would be, not really. The DNA doesn't rule it out, it just doesn't demand it. That's where archaeology re-enters the story, because genetics gives you this big, smoothed-out, species-wide picture. Archaeology gives you snapshots, specific places, specific times, specific people leaving tools and bones and hearths. Sometimes they line up beautifully. If genetic models say a population expanded rapidly in a region around 50,000 years ago, and archaeologists see a sudden explosion of sites and new technologies there at the same time, that's a strong convergence. Two independent lines of evidence telling the same story. Other times, they clash. When early bottleneck models suggested humanity was reduced to a tiny remnant around 74,000 years ago, some archaeologists went to the layers bracketing Toba ash in India and Southeast Asia, expecting to see an obvious break. Rich tool assemblages before, emptiness or radical change after. What many found instead were more complex patterns, some continuity in technology, some signs that local groups survived and kept doing what they'd been doing. Not everywhere, not uniformly, but enough to make the almost everyone died version look too simple. That tension between a dramatic genetic story and a more mixed archaeological record is one of the reasons the field has shifted toward a more cautious view of the Toba bottleneck. When the two records agree, we can be fairly confident. When they disagree, it forces us to re-examine our assumptions on both sides. Are the genetic models oversimplified? Are we misreading the tools? Is there some third factor, like migration or population structure or unsampled regions, that reconciles them? With Toba, the balance of evidence today suggests a compromise. Yes, our species has a low diversity past with real bottlenecks. Yes, Toba was a huge eruption that must have been devastating in some areas. But no, we can't yet say with any real precision that it single-handedly drove the species down to a few thousand survivors. Instead, Toba looks less like the one villain, and more like one of several heavy blows landing on a species that was already numerically fragile and geographically fragmented. To figure out how fragile and where the blows landed hardest, we have to zoom in. Genetics can tell us that some lineages squeeze through a very narrow channel. Archaeology and geology can tell us where some of those channels might have been on the map. Which raises the next big question. If Toba really did blacken skies and chill climates across half the planet, where were the places that still had enough light, warmth, and food for humans to hang on? Where, on a darkened Earth, was survival most likely? To answer that, scientists use a concept with a slightly poetic name, refugia. Refugia are the good enough places in a bad time. Not paradises, just patches of the world where conditions are a bit less terrible than everywhere else. A little less cold, a little less dry, a little less buried in ash. Places where plants still grow, animals still feed, and small human groups can keep doing what humans do, hunt, gather, share, have children, while vast regions around them go quiet. They're the environmental equivalents of those last green oases you see in satellite images of advancing deserts, thin lines of river forest, wetlands in a dry plain, a narrow coastal strip that keeps catching fog when the inland is bone dry. The trick is, refugia are not obvious from a global climate curve. You can look at an ice core and see the average temperatures plunged, but that doesn't tell you where. On the ground, a band of 30 people could still dig tubers, catch fish, and find drinkable water. So researchers take a different approach. They combine climate models of the Toba period, maps of ancient coastlines, reconstructions of vegetation, and the scattered archaeological sites we do have, and ask, if you were a human living through this, where would you have had the best shot? One of the first big candidates on the table is Africa. In a lot of older discussions, you'll hear a kind of shorthand. Africa was the refuge. People outside Africa got hammered. The survivors were mostly African. There's a grain of truth here. Modern genetic diversity is highest in Africa, which points to big, long-lived populations there. But the reality is messier and more interesting. Africa is not one climate. It's many. During the late Pleistocene, when Toba erupted, different parts of the continent were doing very different things. Some regions were drying out, others were relatively wet. Some were cooler than today, others were buffered by ocean currents or mountain ranges. North Africa, for example, has swung back and forth between green Sahara phases with lakes and rivers, and hyper-arid phases where it looked more like the Mars landscape we're used to seeing now. East Africa's rift valleys have cycled through deep lakes, shallow swamps, and salt flats as rainfall belts moved north and south. Southern Africa has its own complex dance of coastal fog, interior drought, and shifting vegetation. In that patchwork, certain regions stand out as plausible refugia, not because they were untouched by Toba, but because they had built-in buffers. Coastlines are one of those buffers. If you hug the coast, your food web doesn't depend solely on rainfall inland. You've got fish, shellfish, seaweeds, beached carcasses, birds, and plant communities nourished by sea fog and groundwater. Even in cooler, drier climates, the ocean keeps delivering energy to the shoreline twice a day. There's growing evidence that some early Homo sapiens populations were already using coastal resources heavily before and around the time of Toba, especially along parts of eastern and southern Africa. Shell middens, fish bones, and sophisticated stone tools from sites like Pinnacle Point and Blombos Cave in South Africa cluster in roughly the right time window, though exact dating relative to Toba is still debated. Here's where sea level enters the story. At the time of Toba, global sea levels were significantly lower than today because more water was locked up in polar ice. That means the coastlines our ancestors walked on are now drowned tens of meters below the modern sea surface. If you think humans were clinging to narrow coastal strips, that's exactly where their camps, hearths, and refuse piles would be, on real estate that later disappeared underwater. From our perspective, that creates a bias. The places that might have been prime refugia during and after Toba are also the places least likely to preserve accessible archaeological evidence today. We're trying to reconstruct survival strategies while a huge fraction of the relevant landscape is literally off the map. Still, we can make educated guesses. Equatorial and near-equatorial coasts, especially those influenced by warm currents, look like strong candidates. They tend to have relatively stable temperatures, even when the global average falls. They often support productive marine ecosystems, and they sit under atmospheric circulation patterns that, while they can shift, don't usually cut off moisture entirely. Stretch a thin but continuous strip of okay enough habitat along such a coast. Sprinkle in estuaries, river mouths, and rocky shores full of tide pools, and you've created a string of pearls, a chain of small linked refugia where groups can move, split, meet, and exchange knowledge over generations. Inland water is the key. When climate deteriorates, whether from volcanic aerosols, changing monsoons, or broader glacial cycles, the first thing to fail for humans is often not temperature, but water and food. And water, on land, is rarely evenly distributed. Rivers, lakes, and wetlands become lifelines. They concentrate what's left of the productivity in the landscape. Even in semi-arid regions, a permanent river can sustain gallery forests and floodplain grasses. Lakes can hold fish, birds, and plant foods long after the surrounding land has turned to dust. Seasonal wetlands can still pulse with life part of the year, giving people something to move toward predictably. In Africa, the great river systems, the Nile, the Niger, the Zambezi, the Congo, and their tributaries would have been magnets during stressful times. So would smaller basins, rift valley lakes, endorheic basins that periodically filled, and upland marshes fed by mountain rainfall. There's a similar pattern outside Africa. In South Asia itself, even if vast tracts of forest and grassland were devastated by ashfall and drought, river corridors like the Ganges, Brahmaputra, and their ancestral systems could have offered partial shelter, once conditions stabilized enough for vegetation to return. In Southeast Asia, the now drowned Sunda Shelf would have supported broad lowland plains with rivers and coastal wetlands, potential refugia whose archaeological traces are now under the Java Sea and the South China Sea. Again, the problem is that we're trying to read a story with many of the pages torn out or soaked beyond legibility. Climate models suggest one picture of where rainfall held up and where it collapsed after Toba. But those models depend on assumptions about how much sulfur the volcano actually pumped into the stratosphere, how long the aerosols persisted, and how regional monsoon systems responded. Change those inputs, and your map of good and bad zones shifts. Lake sediments and pollen cores add local detail. In some African lake basins, we see signals of cooling and drying in roughly the right time frame. In others, the record is more muted. Marine cores off various coasts show changes in dust and plankton that hint at wind and nutrient shifts. But connecting those changes directly to human experience, this valley dried out enough that everyone had to leave, is still more inference than certainty. Archaeology supplies snapshots. In a few places, like parts of East Africa and South Africa, stone tool traditions seem to persist through the Toba interval, without an obvious break. That's consistent with the idea that local populations survived in place, perhaps using rivers, lakes and coasts as buffers against wider climate stress. In other regions closer to Toba, the archaeological record is thinner or harder to date. Some sites in India show apparent continuity of tools across the ash layer. Others are ambiguous. Others are missing entirely, perhaps because erosion stripped them away or later sediments buried them deep. Put all that together, and you get a map of likely refugia that looks more like a draft sketch than a finished product. Clusters of potential safe-ish zones in eastern and southern Africa, possible refugees along the African and Arabian coasts of the Red Sea and Indian Ocean, river and lake basins scattered through the continent's interior, maybe patches of Southeast Asian rainforest and coastal lowlands that, while hit, were not completely sterilized. Perhaps some sheltered corners of East Asia less affected by the worst of Toba's climatic punch. But every one of those candidates comes with asterisks, dating uncertainties, gaps in the record, the ever-present possibility that our models are missing some key piece of the puzzle, like how fast ecosystems recovered locally, or how much mobility humans really had under these conditions. Refugia modeling, in other words, is a kind of educated storytelling anchored to physics and fossils. We know that humans at the time were not everywhere. We know that climate and ash would have hit some regions harder than others. We know from many other species, plants, animals, even microscopic plankton, that during extreme events survival often depends on small, scattered refuges rather than broad, uniform safety. So it's reasonable to imagine our own ancestors doing the same thing, clustering along watery corridors, clinging to equatorial belts, shadowing coastlines, retreating to places where local conditions blunted the worst of the global shock. But we should be careful not to turn those reasonable inferences into rigid maps. Any neat graphic you've seen of human refugees during Toba is built on layers of assumptions about eruption magnitude, aerosol spread, climate sensitivity, habitat response, human diet breadth, and mobility. Shift any of those and the bright green safe zones move. And that uncertainty matters for our story. Because where people survived shapes what happened afterward. Which lineages expanded, which technologies were preserved, which routes were open for later migrations. If the main refugia were in southern Africa, that sets up one trajectory. If they were spread more widely around the Indian Ocean rim, that sets up another. If inland river basins played as big a role as coasts, that changes how we think about later dispersals into Eurasia. What's clear is that survival, wherever it happened, was not evenly distributed. Some landscapes became dead ends, others became funnels, channels that concentrated people and genes and ideas into a few viable corridors. And from those corridors, once the skies cleared and the climate inched back toward something more forgiving, humans began to move out again. To understand who those humans were and what kind of world they were stepping into, we have to remember something else. They weren't alone. Even in the shadow of Toba, our ancestors were sharing the planet with other kinds of humans. When most people picture early humans, they imagine a single kind of creature wandering around a mostly empty world. That's not what the world looked like when Toba blew. Homo sapiens, our species, or at least our immediate ancestors, were just one branch on a crowded human family tree. And depending on exactly how the dates line up, that tree probably still had several living branches when the sky darkened. In Europe and Western Asia, there were Neanderthals, stocky, powerful, cold-adapted humans who had been sculpted by hundreds of thousands of years of glacial cycles. Deep chests, thick bones, big brains, expert hunters of Ice Age megafauna. Farther east, stretching across parts of Central and Eastern Asia, there were Denisovans. We don't know what they looked like in detail. The fossil record is basically a few bones and teeth, but their DNA has turned up from Siberia to Papua New Guinea. That tells us they were widespread, adaptable, and successful. And then there were others. In Indonesia, there had recently been a tiny island-dwelling human, Homo floresiensis, the so-called hobbit, with a brain the size of a chimp's and stone tools that say, "Don't underestimate me." On the Chinese mainland and elsewhere in Asia, there were various archaic populations that don't fit neatly into our modern species boxes, groups sometimes called archaic Homo, late Homo erectus, or given regional nicknames as new skulls and jawbones come out of the ground. The point is, when Toba erupted, Earth was not the planet of the apes and then suddenly the planet of us. It was a planet of humans, plural, cousin species and cousin lineages sharing habitats, overlapping in ranges, sometimes ignoring each other, sometimes trading genes. Toba didn't erupt onto a blank canvas. It erupted into this already busy, already complex human world. So what happens if you drop a massive climate shock into that world? It's tempting to assume a single global answer. Everyone crashed, or everyone muddled through. Reality almost certainly wasn't that tidy. Different human groups were living in very different environments. Neanderthals in Ice Age Europe were already specialists in coping with cold, short-growing seasons and highly seasonal food supplies. Their lives were rhythms of fattening up in brief summers, tracking herds, caching resources, and enduring long, dark winters. If Toba knocked global temperatures down a notch and shifted rainfall patterns, that might have been a stressor. But it was superimposed onto a system already built for extremes. By contrast, some Homo sapiens groups hugging relatively stable coasts or living in equatorial forests may have experienced less temperature shock and more subtle shifts, slightly weaker monsoons, slightly longer droughts, slightly thinner edible plant cover. For them, the immediate challenge might not have been sudden ice age so much as our usual fallback resources are failing more often. Denisovan groups scattered from temperate Asia to tropical Southeast Asia would have faced yet another mosaic of impacts. Some might have been far enough from the main ash plume that the direct fallout was minimal, but still caught in the global climate aftershocks. Altered monsoon belts, disrupted ocean currents, changing plant communities, and the smaller, more localized human lineages, like those on islands, may have been in the most precarious position of all. When your entire world is one or two islands, you don't have much room to dodge a prolonged drought, a failed reef system, or a collapse in the local fauna. Ecology has a cruel rule. Specialists often thrive until the game changes. Neanderthals, for example, seem to have been highly effective at a particular way of life, hunting large game in cold and temperate environments. Their skeletal injuries read like a catalogue of close-range confrontations with huge animals. Their tools and site layouts suggest they were very good at this. But being a specialist hunter also ties your fate tightly to the health of a few key prey species. If a climate shock knocks those populations down, or alters their migration routes, a Neanderthal group can't just flip a switch and become shoreline shellfish gatherers overnight. Technically, they probably knew how to do a lot of things. We shouldn't caricature them. But there are always constraints. Cultural traditions, group knowledge, toolkits, and social expectations all steer what a population does when the environment shifts. Some Homo sapiens groups, in contrast, were already leaning into breadth. In parts of Africa, for example, we see evidence of mixed subsistence strategies, hunting medium and small game, gathering a wide range of plant foods, exploiting shellfish and fish when available. That kind of jack-of-many-trades approach can be a buffer when any one resource base falters. Toba, in this view, wasn't just a volcano, it was a test of flexibility. Groups with wider diet breadth, more mobility and broader social networks might have had more options. They could pivot to new foods, move to new patches, tap into allies a few valleys or days' walk away. Groups that were more rigidly tied to a specific prey, a specific landscape, or a specific seasonal pattern might have had fewer ways to absorb the shock. But here's where we hit a hard limit in the evidence. We'd love to point to a thick layer in some cave and say, look, Neanderthal populations in this region plummeted exactly after the Toba ash appears. Or Denisovan tools vanish from this valley right at the volcanic horizon. So far, the record just isn't that cooperative. Part of the problem is dating. Pinning archaeological layers to a precise moment 74,000 years ago is technically challenging. Different dating methods have different error bars. Sediments get mixed. Layers slump or erode. Ash can be reworked by wind and water. Sometimes what looks like a crisp before and after in a trench is, at the scale we care about, more like before, during, and long after smeared together. Another problem is simple scarcity. We have only a handful of well-dated, well-preserved Neanderthal sites that even roughly bracket the Toba interval. For Denisovans, it's worse. We know most of their story from DNA, not from long-layered cave sequences. For many other archaic human groups, we might have a single skull and a scatter of tools, with no clear stratigraphic context at all. Put bluntly, if Toba did wipe out some regional population of Denisovans or a marginal Homo erectus group on some Asian plateau, we might never know. They could disappear silently from a record that was already thin to begin with. Even where we do see continuity, Neanderthal tool traditions in parts of Europe, Homo sapiens technologies in parts of Africa, it doesn't prove that everything was fine. A stone tool style can survive even if local numbers crash and only a few pockets hang on. Cultural continuity doesn't necessarily equal demographic health. So when we ask, what did Toba do to all these other humans? The honest answer is, the signal is fuzzy. There are hints. Some genetic studies suggest ancient population dips in Neanderthals and Denisovans around glacial transitions, but tying those dips specifically to Toba, rather than to the broader Ice Age rhythms, is speculative. Some regional archaeological gaps might reflect local declines or abandonments, but they might also be chance. Nobody has dug there yet, or the right sediments didn't preserve. Still, even with that uncertainty, one thing is very clear from the genetic story that comes later. Whatever Toba did, it did not cleanly erase our cousins. Tens of thousands of years after the eruption, when Homo sapiens expanded out of Africa in major waves, they met Neanderthals in the Levant and Europe. They met Denisovan-like populations in parts of Asia and island Southeast Asia. And they didn't just exchange wary glances across the valley. They interbred. Modern people of non-African descent carry a few percent Neanderthal DNA. Many populations in Asia and Oceania carry Denisovan DNA, sometimes in functionally important genes linked to altitude tolerance or immune responses. These are the genetic fingerprints of meetings that happened long after Toba, meetings that would not have been possible if those cousin populations had been wiped out entirely by the eruption and its aftermath. That doesn't mean they sailed through unscathed. You can imagine a world where Toba and the subsequent climate swings thin out Neanderthals in some regions, compress them into certain refuges, and perhaps eliminate some marginal Denisovan populations entirely. Then, as climates oscillate over the next tens of thousands of years, those surviving pockets expand and contract again, overlapping at different times with expanding Homo sapiens. The fact that we see multiple episodes of interbreeding in the DNA, distinct pulses of Neanderthal ancestry, distinct Denisovan contributions, suggests that these survivals were not one-off flukes. Different human groups persisted in enough numbers, over long enough spans and close enough proximity, to repeatedly interact. That in turn tells us something about the shape of survival. Toba likely didn't create a single favoured species and doom the rest. Instead, it probably reshuffled the deck. Some regions became harsher, some refugia shifted, some lineages lost ground, others held on or even found new opportunities. Maybe Neanderthals in steppe environments struggled when key herbivore populations dipped, while groups in more mixed woodland steppe mosaics had more buffers. Maybe some Denisovan populations living in highlands were already adapted to thin, cold air and coped better with post-eruption chill than lowland groups that depended on monsoon-fed forests. Maybe Homo sapiens on certain coasts saw less disruption to their marine food webs than inland foragers far from the sea. These are plausible ecological stories. They fit what we know about how climate shocks play out across landscapes and species today. But we should be careful. They are still stories, hypotheses more than conclusions. What they do emphasize, though, is that our ancestors' path through Toba was not taken in isolation. Every decision a small Homo sapiens band made, whether to move, to stay, to switch foods, to gamble on a new valley, was made in a world where other humans were also adapting, shifting territories, and managing their own crises. A safe refugium along a river might not just be attractive to you. It might also attract Neanderthals coming in from the west, or Denisovan-like groups drifting down out of the highlands. When those worlds collided, the outcomes would have ranged from avoidance to competition, to cautious coexistence, to full-on intermarriage and cultural exchange. The genetics tell us that, in the long run, genes crossed those boundaries. The archaeology hints that ideas and technologies did too. So as the skies slowly cleared after Toba, and ash settled into thin grey memories on the landscape, the human world that re-emerged was not a blank reset. It was a patchwork of survivors, different species, different lineages, each tested in slightly different ways, each carrying forward its own mix of genes, skills, and stories. Their overlapping fates would shape the next chapters of human evolution, and for the tiny fraction of Homo sapiens who made it through, the question was no longer just, can we survive this? It was, how do we live and compete in a world where the neighbours are also human? So what does it actually look like day to day to live through the long tail of something like Toba? You can't negotiate with the jet stream. You can't argue with failing monsoons or convince a dying forest to bounce back on your schedule. The only levers you have are your body, your brain, your tools, and the people around you. Start with the most basic question. What do you eat when your world is broken? One of the most powerful survival strategies for any human group, before and after Toba, was diet flexibility. A band that mostly eats one kind of thing, one migrating herd, one seasonal nut, one predictable fruiting tree, lives or dies with that resource. A band that can eat many things has more roll with the punches capacity. In practical terms, that means broad foraging. Not just we hunt big animals, but we hunt big animals when we can, small animals when we must, dig up roots in the dry season, strip bark if we have to, gather seeds, crack nuts, collect insects, raid bird nests, grab shellfish, trap fish. Imagine a Homo sapiens group along an East African shoreline a few years into the post-Toba cooling. Maybe the inland savannas have thinned, the grass doesn't get as high, the herds are restless, the rains are mistimed. That group's fallback might be tidal flats and rocky pools, shellfish, crabs, small fish. During some glacial phases, those coastal foods seem to have been critical buffers. They don't depend as much on rainfall inland. They're not glamorous megafauna, but they keep children alive. Now imagine a Neanderthal band in a cold steppe forest mosaic whose usual reindeer routes have shifted. The herds are still there, but maybe they migrate earlier, or linger further south, or thin out after a bad decade. A group that can kill a mammoth but also snare hares, dig for edible tubers, and exploit riverine fish has more options than one that pours all of its skill into close-range big game hunting. Diet breadth doesn't mean everyone was a perfect generalist. Culture matters. Some groups probably had taboos or preferences that limited what they were willing to eat. Some may simply never have learned particular tricks. How to detoxify a bitter root, how to smoke fish properly, how to avoid poisoning yourself on certain shellfish. But any group that survived repeated bad years was, by definition, leaning into whatever variety it could get. And when variety in a single place wasn't enough, there was another lever move. Human ancestors had been mobile for millions of years, but a disturbed post-eruption world raises the stakes. if rainfall belts shift 100 kilometers, if a lake shrinks, if a forest edge creeps downslope, staying put becomes a gamble. Mobility here doesn't mean wandering randomly. It means knowing, in detail, the seasonal geography of your world, where the last waterholes linger in a dry year, which south-facing slopes keep edible greens a few weeks longer, where a certain root can be dug even when the soil is baked, who, 3 days' walk away, has a reliable spring. You can imagine annual circuits stretching hundreds of kilometers, tweaked constantly in response to new conditions. One year, the group swings wider east to catch a productive river valley. Another year, they cut that loop short because the valley feels empty. Few tracks, thin plant cover, ash still too thick in the soil. Over time, these adjustments stack up into migrations. What starts as, let's just push a little further this year, becomes, a few generations later, a new home range, a new set of neighbours, a new patch of the map where your language and stories take root. For Denisovan-like groups in Asia, that mobility might have included big altitude shifts, dropping out of high plateaus when winters bit too hard, then climbing back when lower valleys dried out. For island lineages, mobility could mean actual water crossings, paddling to a neighbouring island when drought hits, or retreating upslope into cloud forest when coastal reefs crash. Being able to move presupposes knowledge, mental maps, seasonal calendars, shared stories about where the ancestors went in the last bad time. It also presupposes technology. You can't just step into a harsh, cooling, more volatile climate naked and empty-handed and hope to walk it off. Fire, shelter, clothing. These are the buffers that turn a lethal environment into a survivable one. Fire isn't just for warmth. It's a way to cook otherwise marginal foods, making them digestible and safer. Bitter roots become edible. Tough meat softens. Some toxins break down. In a world where your diet is pushed toward whatever you can grab, fire expands your menu. It's also a predator deterrent, a light source, and a social magnet. Even in the best of times, the evening fire is where information gets passed around. Who saw what herd, where the berries were still thick last year? Which path up into the hills is least exposed when the weather turns? In the worst of times, when the landscape feels unstable and threatening, that nightly gathering around heat and light is where shared plans get made. Clothing extends the kinds of environments your body can handle. Neanderthals in particular seem to have been very cold adapted, and there's debate about how complex their tailored clothing was. But whether they were draping hides or sewing them into fitted garments, the principle is the same. Insulation buys you exposure time. It lets you hunt a little longer when the wind sharpens. It lets you sleep away from the deepest parts of caves or rock shelters where damp can kill. It lets you cross passes and ridgelines that would otherwise be off limits to near-naked tropical bodies. Shelter scales this up. A good rock overhang, a cave mouth, or even a well-built brush hut or snow shelter evens out some of the volatility. When ash blows, when sleet comes in sideways, when temperature swings from day to night are brutal, being able to retreat into a somewhat controlled space keeps more children alive through the first 5 fragile winters of their lives. There's even some evidence that people were using fire in more sophisticated ways, managing vegetation, encouraging certain plant communities, driving game. If that's right for some regions, it means that in the aftermath of Toba, some human groups weren't just ducking the weather. They were gently steering their local ecosystems, nudging them toward configurations that met their needs better in a changed climate. That's another kind of buffer, but even broad diets, high mobility, and good fire and high technology only get you so far if you're alone. The thin margin between life and extinction, for our species especially, seems to have run through social networks. Imagine 2 bands in neighbouring valleys, each with 20 or 30 people. In a normal year, their paths cross occasionally. Maybe they trade some stone from a good quarry for shells from a distant shore. Maybe a young woman from one group marries into the other, knitting a new thread into a loose alliance web. Now imagine 3 terrible years in a row. The animals are thin. The fruit is late. The ashfall in one valley is just thick enough to suppress key plants. In the other valley, it's more patchy. If those 2 groups are strangers or rivals, each must ride out the storm alone. If they are entangled through kinship, trade, and shared rituals, new options appear. People can move. A few families can temporarily join the less hit group. Food can be shared unevenly. We have more this year. We'll remember that your people carried us through 3 summers back. Knowledge can move. One group teaches another how to process a new plant, how to find water in a type of rock they'd never bothered to explore before, how to stitch a tighter seam in a hide coat. Archaeologists see hints of this in the wide distribution of similar tool styles over large areas, in the spread of particular raw materials far from their sources, and in genetic signatures that look like structured partner exchange rather than random mating. None of that is specific to Toba, K2. But in a stressed world, those same social habits become survival infrastructure. Networks can also reroute people away from dead ends. If a Denisovan band hears through rumour chains that a certain plateau has gone bad, waterholes fouled, plants failing, before they arrive they can avoid pouring their dwindling numbers into a doomed landscape. Information in that sense becomes as important as calories. Of course, none of this makes survival safe, or clean, or inevitable. Resilience is not a heroic montage where everyone bands together and wins. It's messy. It means some bands starve while others squeak through. It means groups that manage to keep their networks intact have a statistical edge, not a guarantee. For every lineage that threads its way between famine years via clever foraging, timely moves, and well-timed alliances, another lineage probably miscalculates, stays too long, moves too late, trusts the wrong neighbour, clings to a hunting tradition that no longer matches the animals on the ground. When we talk about pathways of survival in the aftermath of Toba, we're not talking about a master plan that our ancestors consciously executed. We're talking about a swarm of local experiments, thousands of small decisions, what to eat, when to leave, whom to help, whom to attack, which old rule to bend because the weather doesn't behave anymore. Most of those experiments failed quietly. Entire family lines vanished without leaving a trace in the patchy archaeological record. Whole dialects and mythologies, all their names for stars and rivers, winked out. But some combinations of strategies work just well enough, in just enough places, for just long enough, that we're here to speculate about them. Flexible diets kept options open when familiar foods faltered. Mobility let people chase shrinking patches of habitability and discover new ones. Fire, clothing and shelter widened the envelope of what habitable even meant. And social networks of trade, marriage and shared knowledge spread risk and information across space so that one valley's disaster didn't always become one valley's extinction. None of that made the aftermath of Toba anything but brutal. It just meant that, in the cracks of a wounded climate system, there were still narrow ledges where human life could hang on. And if those ledges were real, if people really did survive by stringing together these kinds of strategies, then Toba may have done more than threaten us. It may have quietly sharpened the very traits that would later let our species take over the globe. That's where we turn next. What did living through that kind of pressure cooker actually do to human evolution, culture, and the balance of power between all those different human cousins? When you squeeze a species, you don't just reduce its numbers, you rearrange its future, put enough pressure on a population, and you start to change which ideas survive, which traditions stick, which genes make it through the gauntlet. That's the core of the Toba changed everything hypothesis. Not that the volcano rewrote our destiny in a single blast, but that it nudged the deck and altered which cards were still in play afterward. Start with culture. Imagine a world where some bands are very conservative. We've always followed this herd path. We've always fished this river. We've always married within these 3 neighbouring groups. That kind of stability can work brilliantly in a steady climate. It can even be a strength. Deep knowledge of a particular landscape, finely tuned rituals that match predictable seasons. Now drop Toba into that world, or any serious cold shock. Rains shift, plants miss their normal blooming windows, herds don't come back to the same valleys. Suddenly the groups that cling hardest to the old calendar are at a disadvantage. Their sacred migration route is now a road to nowhere. Meanwhile, somewhere else, a slightly more experimental band is willing to do something that would have sounded crazy 2 generations earlier. Push across a mountain pass they've always avoided, stay longer on the coast than tradition allows, accept strangers into the group because numbers are low. In a stressed world, those rule breakers might be the ones whose children live. Over hundreds of hungry years, that process acts like cultural natural selection. Traditions that help you cope with volatility, flexible hunting practices, broader sharing networks, more permissive rules about who can join your group, tend to stick around because the groups that use them are the ones still telling stories. Traditions that lock you into a narrow, brittle way of life tend to disappear along with the people who keep them. You can see hints of this in the archaeological record after big climate swings. Toolkits get more varied in some regions. Raw materials start moving longer distances, suggesting broader exchange networks. Seasonal movements grow more complex. None of this has a label that says made after Toba, but it's the kind of pattern you'd expect if people who were good at improvising had a survival edge. Now scale that up from bands to whole regions, and you start to see how an eruption far away could, indirectly, redraw the map of human migration. A big volcanic winter doesn't need to kill everyone in a continent to have lasting effects. It just has to turn some familiar corridors into bad bets. Think about South Asia, sitting downwind of Toba. If even a fraction of the ash fallout and cooling scenarios are right, a huge swath of what had been decent habitat could have turned marginal for a while. Dustier soils, unstable monsoons, vegetation in flux. That doesn't mean empty, but it might mean harder to live in than before. For a band moving out of Africa toward the east, that matters. Maybe the most obvious, low-altitude, river-following routes through India become tougher. Maybe inland basins that once offered reliable water and grazing become saltier, or clogged with ash. A path that looked like the easiest way to East Asia before the eruption might, after a few bad centuries, look like an endless series of disappointments and detours. Populations don't need a map to respond to that. They just need a few too many failed seasons in a row in a given direction. Over time, the lineages whose wanderings tilt a little north, or hug coasts a little more, or cling to certain refuges instead of pushing across damaged plains, are the ones that successfully expand. Toba, in that sense, might have been less a wall and more a gentle hand on the steering wheel, subtly shifting which migration routes were most attractive, and therefore which genetic lineages spread where. And that brings us to genes. Whenever you shrink a population, you don't just make it smaller, you make it weirder. In a large, stable population, rare genetic variants mostly drift along slowly. Some spread, some fade, but the law of big numbers means change is gradual. In a stressed, shrinking, fragmented population, chance plays a bigger role. Genetic drift speeds up. Picture 3 small groups scattered across a stressed landscape after Toba. In one, just by coincidence, a few people carry a gene that slightly improves cold tolerance, or starch digestion, or resistance to some respiratory infection that thrives in dusty air. In another, that variant isn't present at all. In the third, it's there, but those carriers happen to die in a rockfall or a conflict. Fast forward 1,000 years. If only the first group leaves many descendants, because they got lucky with local conditions, because their network stayed intact, because they chose good migration paths, then that one little genetic quirk suddenly looks much more common in the region. Not because it was destined, but because a bottleneck magnified the influence of whoever squeaked through. That's what biologists mean when they say bottlenecks can accelerate drift and change which lineages persist. It's not just selection, survival of the fittest, it's survival of whoever happened to be standing in the right place when the ash fell and the climate swung. If Toba did cause serious population contractions in some regions, it could have reshuffled the genetic deck in exactly this way. Whole branches of the human family tree may have been trimmed back or pruned off. Others, which might have remained minor side branches in a calmer world, suddenly became main trunks simply because their carriers happened to live in more buffered environments. When we look at our DNA today and see signs of past bottlenecks, that's the kind of process we're inferring. Not a single cinematic die-off, but a long period when chance and local survival advantages had an outsized impact on which ancestries made it into the deep future. Does that mean Toba directly created the later out-of-Africa expansion around 60,000 years ago, or set the stage for modern humans to outcompete Neanderthals and Denisovans? That's where the story gets slippery. It's tempting to line up the big events, Toba around 74,000 years ago, modern human expansions tens of thousands of years later, and draw a straight arrow between them. Volcano nearly wipes us out. The few survivors carry special traits. Those traits eventually let us conquer the world. It's a clean narrative. It feels right. But evolution and prehistory are rarely that neat. What Toba might have done, if it was severe enough, is add another layer of filtering during a time when our species and our cousins were already dancing on the edge of climate chaos. It may have trimmed some lineages, nudged others into new territories, and slightly altered the palette of genes and cultures that were available when conditions later improved. When modern humans begin their big expansions out of Africa tens of thousands of years after Toba, they're not starting from scratch. They're starting from whatever mix of survivors, traditions and genetic variants managed to carry through every previous crisis. Glacial swings, regional droughts, and yes, possibly super-eruptions. If Toba tilted that mix even a little, favouring certain foraging strategies, body types or social structures in particular regions, its fingerprints might still be buried somewhere in the patterns of variation we see today. But teasing that out from all the other forces at work is incredibly hard. It's like trying to identify one specific storm in the long-term shape of a coastline that's been eroding for millions of years. Interestingly, it's not just our ancestors who are changed by this process. Our understanding of Toba has gone through its own kind of bottleneck and expansion. When the idea of a Toba catastrophe first took off in the 1990s, it was dramatic. A single eruption nearly wipes out humanity, forcing us through an incredibly narrow genetic bottleneck. It was a powerful explanation for why modern humans seem so genetically similar and why our population history shows signs of past shrinkage. For a while, that narrative dominated. It was clean, it was testable, it pulled together volcanic evidence, climate proxies, and DNA. It was the scientific equivalent of a blockbuster story. Then, over the next 2 decades, more sites came online. Archaeologists dug through ash layers in India and found stone tools below and above them, with no obvious break. Paleoecologists pulled longer, higher-resolution records from lake beds and marine cores, seeing that Toba's effects, while real, might have been patchier and shorter-lived than the most extreme models suggested. Geneticists refined their methods and began to see multiple bottlenecks at different times, not one single apocalyptic squeeze. Each new piece of data was like a small band of hunter-gatherers wandering into the conversation with its own local story. Some supported a harsh global impact. Others suggested a tough but survivable regional crisis. As those stories accumulated, the original simple catastrophe model started to look too rigid. The debate evolved. Many researchers now lean toward Toba being serious but not species-ending, a major blow to some regions, especially downwind, layered on top of an already volatile Ice Age climate. Others still see room for a deeper impact, especially if small scattered populations were already under stress. The conversation has shifted from did Toba nearly kill us to where and for whom and for how long did it really matter? In that way, the science mirrors the survival strategies we talked about earlier. The field stayed healthy not by clinging to one elegant story, but by staying flexible, incorporating new evidence, revising old assumptions, and allowing multiple possibilities to coexist while the data catch up. So what did Toba actually change? It may have pruned some branches of the human family, reshaped cultural landscapes in South Asia and beyond, altered migration routes in subtle ways, and tweaked the genetic composition of the populations that later spread across the Old World. It may have acted as one more intense filter in a long series of filters that shaped who we are. Or it may have been, on the human side of things, a severe but local and regional crisis, devastating for the people and ecosystems in its shadow, yet just one of many challenges that our scattered ancestors learned to ride out. The ash layers and ice cores and gene sequences don't yet give us a final verdict. They give us hints, constraints, patterns, and puzzles. They tell us that the world did not end in 74,000 BCE, but they don't fully agree on how close we came, which leaves us with an open question that's almost impossible to resist. When we look at our own faces in the mirror, our shared genetic heritage, our capacity for culture and adaptation, are we seeing the distant echo of a near extinction, or the scars of a brutal, regionally focused disaster that we managed barely to root around? Either way, one thin layer of ash, buried in rocks and sediments across half the planet, marks a moment when the future could have gone very differently. And that thin line holds a lesson, not just about what happened back then, but about how we think about catastrophe, resilience, and our place in a world that can still change faster than we'd like. When you zoom out beyond the arguments and the error bars, a few things stand out as solid. First, there really was a monster. Toba was not a metaphor, not a hypothetical. It was a real volcano, on a real day, that blew a real hole in the world. It threw out thousands of cubic kilometers of material. It laid down an ash sheet you can still trace from the Indian Ocean to East Africa, from the Bay of Bengal to the South China Sea. It punched sulfur into the upper atmosphere and dimmed the sun. The climate system noticed. Ice cores, lake sediments, and ocean mud all show disruptions around that time. Shifts in temperatures, in rainfall patterns, in dust. Not a neat identical signal everywhere, but enough to tell us the eruption mattered on a planetary scale. Somewhere on Earth, people watched the sky go wrong and the seasons misfire. Beyond that, though, the picture blurs. We don't know how many of those people died. We don't know whether humanity as a whole was pushed to a razor-thin edge, or whether severe crashes were mostly confined to unlucky regions under the ash plume and in downwind monsoon systems. We don't know if the genetic bottlenecks we see in our DNA line up tightly with Toba's timing, or if they reflect a messier story, multiple squeezes at different times in different places as Ice Age climates lurched and shifted. We don't know which specific valleys went quiet and which coastlines hummed along relatively unbothered. We can't yet map, village by hypothetical village, who endured steady, if colder rains, and who watched their entire foraging calendar collapse. The truth is probably complicated. Some regions likely suffered catastrophic short-term shocks, crop plants failing in the wild, grazing grounds smothered in ash, river systems choked and rerouted. In other regions, the same eruption might have shown up as a couple of dimmer summers, tougher but survivable if you already had diverse food sources and flexible social networks. The global near-extinction picture is one extreme. The barely noticed it picture is another. The real story of Toba, as far as we can tell today, lies somewhere in between. A colossal geological event layered onto an already unstable climate, reshaping some human futures sharply, others more gently. But here's the part we can be fairly sure about, even if the details stay fuzzy. At least once in our deep past, and probably more than once, our species and our cousins lived through environmental swings and disasters that make modern history look tame. Ice sheets advanced and retreated. Rain belts jumped hundreds of miles. Whole ecosystems reorganized. Super-eruptions like Toba punched the atmosphere. Sea levels rose and fell enough to redraw coastlines, floodland bridges and strand populations. And still, somehow, people got through. Not because they had a plan, not because anyone understood orbital forcing or sulfate aerosols. They survived because of a handful of traits that keep showing up whenever we push into a new environment or ride out a new crisis. Flexibility, the willingness to change routes, diets, alliances, curiosity, the impulse to walk over the next ridge, to ask what happens if we try this plant, this tool, this way of sharing, cooperation, the ability to hold together as a band when things go bad, to welcome outsiders when numbers are low, to trade information as well as objects, and memory, stories about what worked last time the rains failed, or where your grandmother's people went when the big animals didn't return. The thin ash line from Toba is a geological reminder that the world can change very fast. The fact that we're here, arguing over how bad it was, is a biological reminder that our lineage is unusually good at surviving those changes, sometimes by the skin of its teeth. That doesn't mean we're invincible. It doesn't mean modern climate change or other human-driven disruptions are nothing to worry about, because we've been through worse. Past resilience isn't a guarantee. It's a warning label. Our ancestors had no choice but to adapt or disappear. We, uniquely, have the power to push the system toward crisis or away from it. We can trigger our own volcanic winters in slow motion, or we can use the same intelligence and cooperation that got us through natural catastrophes to prevent the worst of the ones we're creating now. When you think about Toba, don't just picture the ash and the cold. Picture a handful of families in some sheltered valley or along some windswept coast doing what humans always do when the script falls apart: improvising, trying new foods, making new tools, calling in old favours, telling frightened children that somehow spring will come back. Every person alive today is in some small way an heir to that stubbornness. If you enjoyed exploring this deep prehistory, these hidden turning points that almost went the other way, take a moment to support the channel. Please like the video, subscribe if you haven't already, and let me know what you think in the comments. I'd really love to hear where you're listening from in the world, especially knowing how far our species has travelled since those ash-darkened days. And if you want to dive even deeper into the strange, fragile, almost lost chapters of our past, I've put together a whole book of prehistoric secrets and near misses, stories like this one that hide in bones, sediments, and DNA. You can read more about it and grab your own copy at sleepytimehistory.com. Because somewhere, in a layer of ash under our feet, is the quiet proof that the future is never guaranteed, and that sometimes, against the odds, a few scattered survivors can carry the whole story forward.